So we're starting with true false. I'll use the polls to the time. So the first one is A. Aldol reactions rarely undergo dehydration/condensation. And I'll describe what I mean, but feel free to put what you're thinking. If you do catalytic hydroxide with an aldehyde, it can do an aldol reaction. And here it will lead to something like this. And then it can also keep going after the aldol product. And this last one is the dehydration product. So the question is basically saying that most of the time you're not gonna form this. This doesn't happen very often, if that helps at all. I'm gonna go ahead and end it there. Most of you said it's false, which is correct. It is false. The majority of the time, this last step, the condensation, like it happens spontaneously. You can't really stop it. So the fact that it's spontaneous, it happens most of the time, means it happens a majority of the time. It's not rare at all. There are rare cases where it wouldn't happen at all. Okay. Next one is B, which is cannot form an enolate at a tertiary alpha position. And ahead of time, I'll admit the wording probably could be a bit more clear on this. I will draw like a potential example. Something like this is alpha 2-carbonyl and it's tertiary. So basically, true or false, can you form an enolate there at that alpha spot? I'll give it 10 more seconds or so. Okay. So, like I said with the drawing, this spot is tertiary. This happened yesterday too. So if there's something in the book or Dr. Okuda said something in lecture that says you can't form enolates here, then just go with what he said. But I haven't looked at the book in a long time and I haven't seen the lecture from today. If he said you can't form enolates at spots like this, but there is one hydrogen here at this alpha position, and all you need is one hydrogen to form an enolate. So saying you cannot form an enolate, I would say is false because there's a hydrogen there. Again, if you read or heard something different, then tell me or just go with that if you don't want to tell me. But I assumed because one hydrogen, it would be able to form. Just need one alpha hydrogen to form that, so it is false. Next one is C, malonic ester synthesis is a base-promoted reaction. Is that true or false? And that's opposed to base catalyzed, so just consider how much base you would use for that reaction and if it's regenerated or not. I'll give it 10 seconds from now. Alrighty. So most of you said it's true, which is correct. Because remember, a malonic ester, I'll draw an example. I'm not going to do the whole reaction, but it has two esters beta to each other like this, like that's the starting material. And then you add one equivalent of base, and then you add something with the leaving group, acid and heat. Not all of these are relevant to this question, but just as a bit of review, like that's the stuff that goes on the arrow. And it's this part on this first step where we're adding one equivalent of our base. That's why we would say it's base promoted. If it was base catalyzed, you wouldn't need a full equivalent. You would use a catalytic amount, like you see here and here, and it will be specified. So yeah, that's how you can tell it's base promoted. And the last one is D. Dehydration of an aldol product can occur under acidic or basic conditions. And this might not be the case on exams, but there is something on this worksheet, like one of the problems, that might help you figure out the answer to this, if you're not sure yet. I'll give it 10 seconds. Okay. Majority of you said it's true. A couple did say it was false. I'm gonna go ahead and erase the screen so I can scroll down and it won't be a cluttered mess. So just warning you about that. I can pull that stuff back up if you do have a question. But this is a dehydration reaction because we're going from this aldol product you start with to that dehydration product. And this is done under acidic conditions, and it is a thing that can happen. So this one was true. And this is just an example that could have helped you recognize that. Most of the time it's done under base conditions because like when you're doing aldol, you're starting with this catalytic base already. So the base is already there. But if you wanted to, for whatever reason, you can also do it with an acid. And you should be aware of that. So that is the true or false. Now the next one, and again, like I haven't seen the lecture from today, so I don't know what exactly the limit of the exam is for Thursday. But I remember him saying last week that the limit was Aldol reactions, so You guys can let me know whether or not like this is gonna be on the exam or not, but like this is mixed aldol, like that's what this topic is. I'm assuming like he talked about it today, whether or not it was on the exam. He probably said if it was. Dehydration is the limit. Okay. I guess you don't have to worry about this then. So like you will have to know it for the final. So pay attention to that. But I guess all the stuff on mixed aldol, like question 2 and 3 are gonna be on this. Don't stress about for the exam. I didn't know where he would stop, so that's my bad. But yeah, I'm assuming you guys saw this either way. So this is like a mixed aldol reaction where we have 2 different carbonyls and we're adding catalytic base to form an aldol product. And the products that I showed here is what would form if we had this enolate from the ketone and it attacked the aldehyde. And this isn't the full mechanism, but this is like a summary or just the nucleophilic attack to show the bonds forming. And then you would get this product. But I'm hinting that there's something wrong with it. There's one product shown, but others are going to form. And how can they form? Like, can anybody describe what else could happen besides the enolate here attacking the aldehyde? Like, is there anything else this enolate I have drawn could attack? And if this isn't super familiar, that's okay, because it won't be on the exam. But remember, like in a regular aldol, if I didn't have that aldehyde drawn, you would be assuming that the ketone would react with another copy of itself. And this is still possible if you have a mixed aldol reaction like this. There's still neutral forms of the ketone floating around that this same enolate can attack. It can attack another copy of itself, basically, and ignore the aldehyde. And that would lead to a different product. So that's what the enolate from the ketone could attack. But is that the only enolate we could form? Do we have any other alpha hydrogens that we could use with what we've been given?
You mean just on the first ketone?
Maybe not on the ketone, but what else can we work with? Yeah, Andy said it, it's on the aldehyde. Remember, there's a hydrogen here that's alpha to the aldehyde. So we can also form an enolate here. And then this enolate could react with the other ketone. So do something like this. Get this product. And it could also react with another copy of itself, a neutral aldehyde. And again, like these arrows I'm drawing aren't full mechanisms. So if you were asked to show an aldol mechanism on an exam, don't show this. This is a step of the mechanism, but it's not the whole thing. So don't put that on a mechanism question. But there are 4 products you could form. And then these all could also do dehydration to give those conjugated enone structures. I'm not going to draw those because that would just take a lot of time, but that's like doubling the amount of products basically. There's a lot of stuff that could form. So multiple. And that's an issue because if you're trying to do this in the real world and like if this was all you wanted, you're also going to form all of this other stuff. And then that just makes it really difficult to get what you wanted and only what you wanted. So this isn't a very practical reaction. And again, don't worry about this for the exam, but like when it comes to the final, you should be aware that like this is an issue and it's like, it is a reaction you can do and you should be aware of how it would go, but there are better ways to do mixed aldol reactions, which we'll go over in a minute. So I'm going to go ahead and move on. If any questions about this, let me know. Go back. It's like I was just saying, these are also, some of them are mixed aldol reactions. Like this first one has one aldehyde and one ketone, two different things with catalytic hydroxide. So that's what we're going for. And we were just discussing how like if multiple enolates can form, then like you're gonna get a mess, you're gonna get a mixture of products. But out of these two structures, which one are we gonna form an enolate at if it's only gonna be one?
Be the ketone, right?
Yeah, because this one, these hydrogens aren't alpha. We don't have any alpha carbons, so those aren't acidic at all. Can only form an enolate here and nowhere else. And then the enolate would mostly attack the aldehyde and give you the mixed product. So I'll do the same thing I've done before. This bond in green is the bonds that we're forming, and then in red is the stuff that we added, like the carbons and oxygen. There's only one carbon in that aldehyde, so it's just like this. But if there were more, I would have put more carbons there. And then unless he's told you otherwise at any point, which if he did, just go with what he said. But unless he said otherwise, I would draw both the aldol and the dehydration product if you get an aldol question on the test, because both are going to form a little bit. We'd see both if you did this. And just a little detail. In this reaction, like the enolate from the ketone could also potentially react with another copy of itself with a ketone up here. But this reaction that I drew is going to be faster because the aldehyde is less sterically hindered, so it's easier to attack. So it's a faster reaction. So even though there's like a potential for a mixture of products, it's a little less likely here because that reaction with the ketone would be much slower. So So it's less hindered, so it will react faster than the ketone. Just in case anybody was wondering why I'm not drawing other products. Okay. Next one is another aldol reaction. So we're adding catalytic hydroxide. This isn't mixed because I'm not putting any other structure here. It's just that one aldehyde. that I'm showing. So as usual, you have to add the base to form this enolate. Like that would be the first step of the mechanism, which I realize I've been doing like a lot. I'm just doing this to kind of show you how things are happening, but the base takes the alpha proton to form these enolates. And then the enolate will attack a neutral form of the aldehyde. Which would look something like this. And I think especially with structures like this one, like where there's a lot of carbons in some weird places, I think it's a good idea to number the carbons. And it doesn't, like how you number it doesn't really matter. You can just number it however you want, whatever you're comfortable with. Like these numbers I'm giving it, this, it might be how you would number it if you were trying to name it, but I'm not doing that consciously. I'm just numbering it to keep track of what is where. So I'm gonna go ahead and erase this. So we're forming a new bond at the alpha position. Then there's an alcohol at the beta position. I haven't said that yet today, but that's like a characteristic of Aldol reactions, which is really important to know. Like this is alpha. The alcohol is always beta to the aldehyde or ketone. No matter what, it's going to be beta if it's an aldol product. And then if I number these, this is 1, 2. Oh, actually, I did that wrong. So kind of glad I numbered it. So hopefully seeing me mess up briefly is actually like good incentive to number the atoms when you're doing these, because it's really easy to miscount or like put an ethyl group or a methyl group in the wrong spot like I just did. And if you don't number it or you don't like triple check, it's very easy to draw the wrong structure. And we talked about like in a true false that a majority of the time you're going to get an aldol product and then you'll also get a dehydration product. But I'll pose the question to you guys. Should we draw the dehydration product with this structure where we form that conjugated double bond with the aldehyde?
I'm guessing no. Usually do, but
And why do you think not here?
because you asked, I don't know.
Well, remember that like to form that, like there's going to be a double bond here where these dots are. So think about how many bonds this carbon I've circled would have if there was a double bond there.
Yeah, okay, I see now.
So yeah, that's the issue. So that's one way you could look at it. If you drew that product, you'd see that carbon has 5 bonds, which is too many. And just for the sake of it, I'll show that here. Like it would look something like this. I'll just put R for the rest of the structure, but you can see the carbon has too many bonds. That does not work. And another thing is, like if you do the mechanism for this, you might remember that we need to form an enolate here to be able to form that condensation product. And to form an enolate, you need a hydrogen, which there aren't any because this spot is quaternary. There's no hydrogens there. So either way you look at it, you can't form the condensation product here. So this is like the only case where it wouldn't happen because it can. Okay. So this is something that might come up on the exam because this isn't a mixed aldol. So just be on the lookout for spots that become quaternary after you form the aldol product. And this is another mixed aldol reaction because we have an aldehyde and a ketone, two different structures. Which one is gonna have the enolate form?
The ketone.
Mm-hmm. Because it has alpha hydrogens and the aldehyde here. This is the alpha position. There's free methyl groups attached, no hydrogens, so you can't form an enolate. So then ketone attacks the aldehyde, and we get our aldol product. I'll show it forming on the right, but it doesn't really matter. So in green is the bond we just formed. Alcohol here. And then that little terpyl group. And again, remember, the alcohol is always on the beta position, beta to the carbonyl. That's always the case for aldol. Don't forget that. It'll make your life a bit easier. And then for the dehydration product, you form a double bond, and then there's still the rest of the structure. And for the dehydration product, it's always going to look something like this. The alkene is going to be between the alpha and the beta carbons. Or you could say it's conjugated with the ketone. Either way you want to look at it, that's how it works. So remember those two characteristics of these products, like beta hydroxy carbonyl or alpha beta double bond. Okay. And last one for question 3. This is another mixed aldol reaction. Which one of these two, the one with the ketones or the one with the aldehyde, is going to have an enolate form?
I think it'd be, I was gonna say aldehyde.
So it does have an alpha hydrogen, but we can consider the pKa's. So like, and this is something you should know for the exam anyway. What should the pK be for this alpha hydrogen next to the aldehyde? And if you guys don't know, I would recommend using flashcards. Like Okuda talked about it on a presentation for class like probably 2 weeks ago now, and he kind of lumped them all into 3 categories with general numbers. So I would just like look for that and then put those on the flashcards and try to memorize it. If you have a hydrogen alpha to an aldehyde, the pK is about 20. And then you also have hydrogens like these alpha to ketones at the end, which also have pKs of about 20. And then I'll do it in a different color. Could anybody tell me what the number of the pK for the one between the two ketones would be? Or if, yeah, 10. I was gonna ask if you didn't know the number, then like, would it be higher or lower? But it's lower, it's 10. If it's between two carbonyls. Like 10 or 11 in that ballpark. And this is if it's between any two carbonyls, you can look at it that way. And that is much lower than the pKs for the other hydrogens. So this is a much more acidic proton. And that means that when we add the base, it's going to react with the most acidic proton. So it's going to form an enolate there. So even though there's alpha hydrogens in both of these structures, only one enolate is going to form, and it's going to be at that red hydrogen because it's the most acidic. And then it will react with the aldehyde and do everything else the same way it normally did. So forming a new bond here. There's an alcohol on the beta position and another carbon. And then you should also show the dehydration product. So as far as I know, this stuff mixed aldol won't be on the exam, but for the final, and maybe I'll talk about it a bit more after the exam, just to refresh you guys, but just in general, to do mixed aldol, you should have one thing with no alpha hydrogens or one thing with more acidic hydrogens. It's like the examples we were doing before this, we had one compound where there were no alpha hydrogens, so it could not make an enolate at all. And then this is a case of one thing having more acidic hydrogens because this spot was more acidic. So that's going to be where the enolate prefers to form. But don't worry about this too much for now. Just take note of it, be aware of it later when you will be tested on it. Okay. Here I have a couple structures and I'm asking which of them could be made from an aldol reaction, and then if it can be, show the starting materials. So I'll just start with the first one. Can anybody tell me if this could be made from an aldol reaction?
Yes.
Are you sure? Where's the alcohol? Like what position?
Oh no, you're right. It's at the alpha position.
Yeah, where should it be?
Beta.
So it's just something to keep an eye out for. Remember, aldol product has OH beta 2. Every time. But this is something he could do to make it look tricky. So it might be good to label the structure to make sure. Since it's alpha, this couldn't be from aldol. How about this next one?
Yes.
Yes, because the double bond is between the alpha and the beta carbons, and that's what a dehydration product looks like. Or you could say it's conjugated, but either way, that's what it looks like. And then if you wanted to work backwards, the bonds that we formed to make this product is the one between the alpha and the beta carbon, this one in green. So to work backwards, you could think of it as just like breaking this bond and then looking at what you get when you break that bond. So like on the left side, this is acetone. So that was one of the starting materials, this ketone. And then on the right side, there's these two carbons. And then where the beta position was in the product, that's where carbonyl is in the starting materials. So I'll put a carbonyl here. And then there's no other carbon, so there's just a hydrogen here. It was an aldehyde. So that's the kind of thought process you could have to work backwards. Break the bond between the alpha and the beta carbon, and then see what you combined to make this. And then, I know I've said it multiple times already, but, and like the exam's not just on aldol, but I think like these two things are important to know because it'll make your life easier with doing these reactions and identifying products and stuff like this. Knowing what the product should look like. Okay. Next one, is this possible to make from an aldol reaction? No, because this is alpha and this is beta. So the double bond isn't on the right spot. It's drawn in a way that makes it kind of look like it, which is something Okuda might do. So be careful that it's not, because it's not in the right spot. And I will say, I didn't have like this exact question, but I had a somewhat similar question on my exam when we had aldols. Like I had to identify aldol products. So like, even if this question isn't asked, like this isn't a useful skill, but that's just to say, he might straight up ask you, like, is this something you could make from an aldol reaction? So, you know, that could be 3 points if you're comfortable with this. And we have one more. So could this be made from an aldol reaction? Yeah. This is alpha to the ketone, and then this is beta. And the alcohol is on the beta spot, which is what an aldol product should look like. So again, this is the bond we formed to make this product. So to work backwards, you can break that bond and then see what you come up with. So on the left side, we have this cyclopentanol or pentanone. And then on the right side, we have one carbon and the alcohol. So that's going to be formaldehyde. Okay. I'm going to go ahead and move on. If you have any questions, feel free to tell me. Go back. Always will be. Here is the acidic dehydration mechanism, starting from an aldol going to the dehydration product. And you should also know the base catalyzed one, which I went over either on the last worksheet or the one before that, when we went over the Aldol mechanism. So be familiar with both. And the first step of this mechanism isn't going to be anything new. It'll be like the same kind of thing we usually do if you add an acid to a carbonyl. So what should we do with this? Like, what should we start with? we're adding an acid. It wants to react with a base. And what does it usually react with when we have a carbonyl? Which oxygen? Just to make sure. Yeah, the carbonyl one. Because there is an alcohol here, but it's going to want to start by protonating the carbonyl oxygen. And then what do we do with this structure where we have a positive charge on the oxygen?
Resonance.
Yeah, resonance. So the first two steps are kind of like intuitive, hopefully, because like this has come up again and again in different contexts. Now, we want to form double bonds there, and we want to kick out the alcohol. And like in the case of base catalyzed dehydration, you would be forming an enolate. So if having base an enolate, like that would be what would be happening in this mechanism. We're adding an acid. So we can't form an enolate because that's negative, but what can we form under acidic conditions that's similar to an enolate? Like maybe similar name, and somewhat similar reactivity.
You know.
Mhm. So be aware of the difference. If you have a base, you can form an enolate. If you have an acid, you can form an enol, but they aren't like, it's always one or the other, but the conditions are important. So the acid conditions here are going to help us form an enol. That's going to be what we want to do next. And we can do that in the first step. We formed water by taking a proton from the acid. So now water can act as a base, take the alpha proton and lead to an enol forming. And then at this point, a couple things happen at the same time. Again, like we want to reform the carbonyl, form this new double bond and kick out the alcohol. So you can push the electrons from the oxygen down to form a carbonyl and then move the double bonds towards the, oh wait, oh, actually, I should do one thing before that. You should turn this into a better leaving group. So it should be protonated first. That's an important step that I might actually have forgotten yesterday. But you protonate the OH, that turns it into water. That's a good leaving group. And then you can do that stuff I was talking about. Push the double bond down to form, or not double bond, push the lone pair down to form a carbonyl. Move the double bond towards the water and kick the water out. And then you're pretty close. You just have this positive carbonyl oxygen that can get deprotonated by water. And give you that final product. So just practice this mechanism, writing it out by hand a few times with different structures. Probably get comfortable with it that way. before I erase this, are there any questions about it? Okay. If I'm going too fast and you have a question, like let me know. I'll go back because this will be important. I don't know if it'll come up, but it's good to be comfortable with every mechanism just in case. This is not new, but it may very well come up on the exam because chapter 21 was like between exam 2 and 3. This is Fischer Esterification. And I will say, like, I can't promise like any one mechanism will be on the exam, but as far as I have heard, I think Fischer comes up almost every time he teaches. So like I guess if you want to know one mechanism and one mechanism only, this is the one to know, but I wouldn't recommend just memorizing one, just in case he doesn't go with it. But I think it's very likely, just as a heads up. And we're adding an acid catalyst, so the first step is the same as what we did last time. You protonate the carbonyl oxygen. I'm going to go over this relatively fast just because I'm a bit low on time. So we protonate the carbonyl, and then you do that resonance form. Same first two steps as the last mechanism. That leads to a carbocation forming, and this is where the alcohol comes in. And it attacks the carbocation. And just as a like little note and a reminder, don't ever like show the alcohol attacking the carbonyl carbon here for the first step. That would be wrong, and you would probably lose a lot of points, if not all of them. I don't know how strict you would be, but that would be wrong to show that as the first step. You have to do the protonation and then the resonance form first. Otherwise, it's not correct. And remember, we do that because the alcohol is not a very good nucleophile since it's neutral. But if you have a carbocation, it's a better electrophile. So that makes it easier for the alcohol to attack. And then once the alcohol has attached, it gets deprotonated, and you can kind of just show the hydrogen leaving since we have acidic conditions. But if you wanted, you could show like another alcohol or Cl minus taking that hydrogen in the last step. And now we basically just want to kick out one of the OHs and reform the carbonyl since we're trying to form an ester. So to kick out an OH, you have to turn it into a better leaving group. So you would protonate it first. That converts it into water. And the water will leave. When the water leaves, it leaves behind the carbocation. Then you can draw a resonance form. That's what this is, pushing the lone pair on the oxygen towards the carbocation to form a carbonyl. And then you would deprotonate the carbonyl oxygen and end up with an ester that looks like multiple bonds. So it is along mechanism, and like it's possible he would ask you to start from the middle, maybe to make it shorter, like starting with this structure, kind of like he started with the hemiacetal in a question on the last exam. I'm not saying he's going to do that. I have no idea. I'm just saying it's a possibility, but you should know the whole thing just in case. And you should know like the other nucleophilic acyl substitution mechanisms from chapter 21, but all of them are very, very similar, just like either protonating and then doing something similar to this, or the nucleophile attacks and then you kick out the leaving group. And you can look in the book and like at past worksheets to see examples of that. But this is like the most complicated. Okay. I'm gonna go ahead and move on, and I'm guessing there aren't any questions because I left a bit of a pause. If there are, let me know, even if it's just clarification. I'll make sure you guys understand the stuff. Here's a structure, and I'm asking to identify the most acidic proton in the structure, and then explain why it's more acidic than the other ones. So can anyone either draw on the screen or like describe kind of where the most acidic hydrogen is in this structure? Yeah, that spot. And why is this the most acidic hydrogen? It is correct, just why?
The pK on that one's the lowest because it's between two carbonyls.
Yeah, the pK is the lowest because the pK is about 10. But is there anything we could consider to explain why the pK is lower? And while I have that question out in the air, I'll just say like pKa for a hydrogen alpha to an ester or any other carbonyl besides an aldehyde or a ketone is about 25. And that also applies to nitro. So that's another number you should know. 10 if it's between two things, 25 if it's anything besides an aldehyde or a ketone, and then it's 20 if it's next to an aldehyde or a ketone. And getting back to this, it is like correct to say the pK is lower, but he might have asked questions like this before where like he asks you to explain why one thing is a stronger acid than the other. And referencing the pK value isn't what he's looking for. He usually wants like a logical reason why the pK is lower. So if you're trying to explain like the more substituted, it is like a tertiary position, but that could be a factor, but there's a more important factor. Remember, when we're trying to explain acid strengths, it's good to consider the conjugate base form, and then, yeah, we're gonna see some resonance if we look at that. I'm just gonna put R for the rest of the structure there to save some time. It's like if we had this enolate coming from that hydrogen I circled, it has one resonance form with the carbonyl on its right, and it has another resonance form with the carbonyl below it. But if we considered like this enolate alpha to the ketone on the left, it's only alpha to that one ketone, so it just has one resonance form. And it's the same idea of the red hydrogen alpha to the ester. It has one resonance form. And remember, more resonance forms means more stable. And in this case, that means it's a weaker base, which means the acid was stronger. Because the stronger the acid, the weaker the conjugate base. So this resonance explanation is why the pK is lower. And if he asked this question, that is what he would be looking for. Like he would want you to draw the conjugate base, show the resonance forms, and say that like because it has more resonance forms, that makes it more stable. So it's weaker and the acid was stronger. And he does like to ask questions like this, so it's good to be able to explain what he's looking for. So are there any questions about any part of this before I erase it and go on to the next page? And I will just remind you guys, like on top of the free pK values I've been referencing today, 25 for like esters and other related things, 10, like if it's between two things, and 20 next to aldehydes and ketones. Don't forget about the old ones. Like you should know about alcohols, water, carboxylic acid, phenol, and then like regular alkyl hydrogens. I think those are the only ones you have to worry about. But don't forget about them because you might be asked to recall those pK values too on the first day. All right, here's a sort of mishmash of reactions. We're starting the first one with a carboxylic acid, and we add sodium hydroxide and then water in one step, and then acyl chloride in the second step. Ignoring the second step, what is the first step going to do to this structure? What are we adding here? Yeah, we're going to deprotonate the carboxylic acid. And it does kind of look like a reaction that would form an ester, but it will be a little different if you were saying that's what the product will be. Yeah, we're adding a base. Carboxylic acid is an acid. So it will do an acid-base reaction. It'll deprotonate the carboxylic acid. Minus. And then in the second step, we're reacting it with this acyl chloride. And you should know like a mechanism you could show for something like this. But remember like carboxylic acids and their derivatives, like the carbonyl can act as an electrophile. And we have a negative charge here, we have a nucleophile. So it can do this nucleophilic attack. And this is not the mechanism. This, like, don't draw something like this on the exam, but this is kind of a summary of what's happening. You're adding the nucleophile and you're kicking out the chlorine, which is a leaving group. But that's not the mechanism. Don't show that on an exam. You have to draw intermediates if you were showing a mechanism. But when we do that, what kind of functional group are we going to form? An anhydride, yeah. I'll show the other part we just added in red. So yeah, this is a way to form an anhydride. If there wasn't a carbonyl here, if that was just an alkyl halide, So like if in the second step we added this, then we would have made an ester. So I saw that that was an idea in the chat, and yeah, like if it was a little different, that's what would have happened. So just make sure to keep an eye out for little details like that that will change the reaction. Okay, next one, we have a ketone, and we're adding 1 equivalent of LDA, negative 78 degrees Celsius, and then we're adding ethyl chloride. What's the first step with the LDA gonna do? Like, what are we adding here? What's it going to form? And yeah, deprotonate the alpha hydrogen because we're adding a base. And which alpha hydrogen is it going to want to take?
The less substituted side
And which side is that here?
would be the right side.
Yep. And this will always be the case. I made a mistake the first time I told you about this reaction. I said it would form on the more substituted side, but remember, Okuda said in class, it forms on the less substituted side when you're doing it with LDA like this. And I don't think you necessarily have to know why. He might ask, but I'm kind of doubtful he would. But this is the structure of LDA. It has those two isopropyl groups attached to the nitrogen. So it's a very bulky base. So it prefers less substituted hydrogens. It prefers less hindered hydrogens, which is why it will take the less substituted one and lead to the less substituted enolate. So it'll form this enolate on the right side. And then we're adding ethyl chloride, which is this. So we're adding an electrophile to our nucleophile. We want a reaction like this to happen. And this is an SN2 reaction. So what kind of substrate is this? Like, is this spot primary, secondary, or tertiary? Just as a check. Primary, yeah. And is that okay for an SN2 mechanism? Yeah. So it's just always good to do that mental check because there are cases, like if this was a tertiary halogen, then this reaction wouldn't work. But if you just assume it's always going to work 100% of the time and you don't check, then you might get it wrong. So just be on the lookout for that. But it works here, so I can redraw that. That's the product you get. And just remember, like I said, this is an SN2 mechanism. Doesn't work tertiary. And just like remember, these conditions are very, very specific, and it's always going to be this for the first step, 1 equivalent of LDA, negative 78 degrees Celsius. So like if you see these conditions, the only thing that could go wrong is if you have a tertiary halogen, but otherwise it's just going to add that alkyl group to the less substituted side every single time. Okay, I'm gonna erase the product here to make a bit of room. Now this next one, we have another ketone and we're adding bromine and then CH3 COOH. What is the purpose of this CH3 COOH? Like, what can it behave as in this reaction? And if you're not sure, you could draw it out and see like what it looks like, what kind of functional group it is. There's a methyl group and it has a carboxylic acid. Yeah, that's the COOH part. So it's a carboxylic acid. It's a strong acid. And what can we do with acid catalysts? Well, I just said it's a catalyst. It's a strong acid, so it's an acid catalyst. What can it help us form with this structure? An enol. Like I was saying earlier, like if you have a base, then you can form an enolate. If you add an acid, you can form an enol. And it's always going to be like that: acid, enol, base, enolate. And just like the last one, there are two spots where we can form an enol. There's like the right side and then there's below it. Where's the enol going to want to form in this structure? Below, yeah. It wants to form on the more substituted side. And that's different from the base reaction, the last one we did, where it formed on the less substituted side. So I'll draw them down here, I guess. These are the two potential enols that we could draw. And the one here on the right, that alkene is more substituted than the other one. And remember, more substituted alkenes are more stable. So this alkene that I've circled is more stable than the other one. And that means like this is going to be preferred. This is going to form faster. And it's going to lead to the major product. So that's going to be the one that reacts. Just to remind you, when you add the base, it adds to the less substituted side because we're using that bulky base. We're using LDA. But for enols, all it cares about is the stability of the alkene. And then it's going to add the bromine to the alpha position. So in the end, we get the carbonyl back. And we add a bromine here. So just remember, like acid catalyzed leading to an enol has different selectivity. It prefers the more substituted one. So the conditions affect where things go. Alrighty. Here we have an acid chloride, and we're adding 2 equivalents of an amine. So I'm just gonna start going through these, and feel free to ask a question if I go too fast, or clarification or anything. But in acid chloride, plus 2 equivalents of an amine will give you an amide. So we're going to replace the chlorine with the nitrogen, and then there should be an ethyl group and an isopropyl group attached, because that's the amine we added. And the 2 equivalents, like you should know the details of why you need 2 equivalents, but it's specific to the acid chloride. So just like remember that that's a specific condition because we're using an acid chloride. Or acid halides in general, I should say. And then the last one on this page, you're giving the starting material and the product, and you have to figure out what reagent to use to complete the reaction. We started with an alcohol and carboxylic acid. And I'll pose this question to you guys. What functional group do we have at the end? What functional group is that in the product? Yep, it's an ester. It's just a cyclic ester. Which you could also call a lactone. And I will say, you should know, like, a cyclic ester is a lactone. That is a term you should know. But it is just an ester. It reacts the same way as an ester, and you form it the same way as an ester. And one way to form an ester is Fischer esterification, which involves adding an alcohol to a carboxylic acid. And that's what we have in this structure. We have an alcohol and a carboxylic acid. They just need the right conditions to react. So that's what's happening here. Once you recognize you're trying to make an ester, just put the right conditions to make these two react, which would be catalytic anhydrous HCl. And then I'm not going to do it here just because I'm low on time, but like if you number the atoms from the nucleophile, the alcohol, to the electrophile, you'll see like it's 6-membered ring and the methyl groups are on the right spots. So the product is correct. You didn't have to change anything else. But on an exam, like that's all you would have to put to complete the reaction. Okay. And the last one is a synthesis problem. We're starting with an ester, and we're ending with an aldehyde and an alcohol. And we added free carbons. We added these carbons here. And is there anything else that jumps out as significant about the product? Yeah, it's an aldehyde, but like, does it look like a product from any reaction that we might recognize?
An aldol?
Yeah. Because the alcohol is beta to the aldehyde. So it's an aldol reaction. Or it could be from an aldol reaction. And that's going to be the way I approach this. It is very possible that you could make this in a way besides using an aldol reaction, but that's probably the most straightforward way to do it. So that's how I'm going to do it. Just again, if you did it another way, that doesn't mean that your way is wrong. I can check it if you would like. But once you recognize that, this is a place where we could like work backwards a little bit. Because if we know we could make this with an aldol reaction, then we can think if we did an aldol reaction, this bond between the alpha and the beta spot is the bond we made to like make this product. So then we can break that bond to work backwards in the synthesis. So then on the top, like this is the top half of the structure. And then you get that aldehyde that I've drawn. And then on the bottom half, we get this aldehyde, which is a mirror image of the blue one I drew. But so it's the same structure, but it doesn't hurt to like draw both just to confirm to yourself that it's the same thing. So these two reacted to form that product. and then you need the conditions to make them react, which is catalytic sodium hydride or sodium hydroxide. And then we have to figure out how to get from the ester to the aldehyde. And we can do it in one or multiple steps. To do it in one step, you could add diba. And then in the second step, you would add acid. And remember, this reagent, diba, is a hydride reducing reagent. That stops at aldehyde. Like if you added LiAlH4 to this, which I'll go ahead and show. So you could add it wouldn't be reduced to an aldehyde, it would be reduced to an alcohol. So if you use diba, it only partially reduces it. It stops at the aldehyde. If you use LiLH4, it goes all the way to the alcohol. But that would be okay. Like if you forgot about diba on the exam, you just remembered LiLH4, you can still work with the alcohol to get that aldehyde. Then you would just want to oxidize the alcohol with a weak oxidizer. So you would use PCC or iodine. Just a weak oxidizer here. But not a strong one like KMnO4. That would give you a carboxylic acid. And there are probably other pathways to do this too. These are just a couple that you might have come up with. Okay, so that's my worksheet. If you have any questions about this or anything else, like I know I'm over the time, but I'm willing to stick around and answer them if you'd like. And that includes like the synthesis, if you've gone over those practice synthesis problems and you want any guidance or anything, like you can do that now, or you can email me later if you would prefer. But yeah, just I'll leave everything up to you. You can leave if you're tired. Do you have any tips or anything to know for exam 3? Besides like what I already pointed out as like specific things that I think are likely to show up, like ranking acid-base stuff and like being able to explain it. And then mechanisms like Fischer will probably show up, but you might be asked about something else too. So mechanisms are good. I haven't really thought about this. I guess just like, I think practicing synthesis problems, if at least if you've like studied a little bit ahead of time, I think synthesis is a good thing to do because like it kind of combines everything in the class. It helps you like work backwards. It makes you consider a bunch of reactions that you might have to use outside of synthesis. And yeah, I just think it's like a good blend of everything. And that's part of why I gave a couple synthesis problems as extra practice, because it's good preparation. Other than that, I would just like review notes and maybe practice drawing mechanisms by hand if you don't feel comfortable with a particular one, because those are important. And notes will help you with conceptual stuff. I know that's like a lot of general stuff, but I hope that helps a little. I'll be here on Thursday, but I won't post a worksheet. So if you want to ask me anything about like class material or just anything else, if you want, like I'll be there the whole time. But if you don't want to come, you don't have to. You won't miss anything in particular. And I'll probably send an email. Yeah, next Tuesday, I'll post a worksheet for that at some point.
Thank you, Nick. See you later.
Good luck. Do you have any last minute? Some workshop? Oh, I sent a message about it. I don't know if you missed it. And I guess if people have been missing them, they won't see this in my recording anyway. Yeah, I'm posting them on YouTube because Canvas, I'm running out of space. I don't know how Okuda posts them without running out of space, but I honestly can't be bothered because I'm only doing this one more semester. So I'm posting them on YouTube. I can post the link in the chat here if you want, or I can send you a message later, whatever you prefer. Actually, I think I'll just send you, yeah, I'll send an email to you right after this. And if you know anybody in the class who happens to not know where to work recordings are, like you can let them know too, because I don't know who doesn't know about this. But yeah, they're all on YouTube. Good luck. Everybody else.